Hello, everybody. Welcome to the Star Trek Online and Science Panel. Muppet Dance. My name is Mike Fatum. I will be your host today. I am the Community Manager for Star Trek Online, and I am also sometimes known as Ambassador Kel on, the internets. And I'm joined by three fabulous guests. He is the Senior Content Designer for Star Trek Online, and designer of the level we'll be mostly discussing today, Gravity Kills. His name is Jesse Heinig. Say hi, Jesse.
Hello! Oh, you told me to say hi, so I'll say hi.
Okay. You could also say hello. It doesn't really matter. Jesse is also being played by the part of the floating head from The Wizard of Oz today. Next up, she is the science advisor for Star Trek, just all of Star Trek, which is kind of amazing. She is also an amazing astrophysicist. Great, cool. Dr. Erin Macdonald.
Hello. Happy to be here. Yay!
And finally, he is known by the probably most misleading title in history. The Bad Astronomer himself has joined us, Dr. Phil Plait. Great to meet you, sir.
Hi. Thank you for letting me be here. This will be fun.
Thank you for being here. We'll just go back and forth on that for the next 10 to 20 minutes. So let's start to talk by talking a little bit about the level we're talking about here. So this is Gravity Kills. It's one of our task force operations. It is a level in which you are battling the vicious Zenkethi on the edge of a black hole, pretty much right next to the event horizon. Jesse, can you talk to us a little bit about your inspiration for this level?
So my inspiration on this actually goes all the way back to the earliest days of video games, to the game Space War, where, they had the ability to model a whole bunch of different scenarios for your stellar conflict, and one of them was that you could have a black hole in the center of the map that was constantly pulling things toward it. And I thought, okay, this would be really a fun bit of gameplay. Take an open space map, because space is big and empty, and throw a black hole in there and make it so that its effects are constantly being felt by the players. So not only are you trying to achieve your mission goals, but you're also having to constantly monitor, how do I not fall into this giant hole in space-time?
How do I not accidentally end up in the mirror universe on Tuesday? Is that one of the ways they've gone to the mirror universe? Now, there've been like 5 different ways. I don't know if a black hole is one of them.
Typically, it's by using the transporter and having a malfunction because there's an ion storm.
Yeah, okay. That makes sense. Science, right?
That's how that went back in time in the original series, I think, using a black star.
There we go.
If I recall correctly.
So now, when you were designing this level, remind me, you were trying to make it as realistic of a black hole depiction as was possible within our engine. How does that work when you're programming something? I'm making the dog typing on keyboard motion for some reason, but
right.
When you're programming a level to have sort of realistic space physics like that, how does that work?
So I actually started by doing the homework and saying, okay, what do the gravitational forces of a black hole actually seem to look like when you look at the numbers that people have hypothesized? And they are obviously very large. So I did just a little bit of back of the envelope calculating and said, okay, I'm going to say that this is kind of a smaller black hole, so that I'm not dealing with absolutely ridiculously over the top masses that can't be handled by a 64-bit computer. And I said, okay, very simple, gravitational formula. We know the gravitational constant. We know the mass of the black hole. And well, for starters, we don't know the mass of the starship that's being attracted to it, which of course affects the forces involved. So, okay, have to do some estimates. We do track like your starship's inertia as a rating, which affects its movement. So I could use that as sort of a placeholder. And then gravity falls off according to a square law. So I decided, okay, I'm just going to actually model these numbers. Throw in, here's the mass, here's the gravitational constant, use inertia as a shorthand for being able to calculate your ship's mass, and then throw this amount of constant force on the player. So they are constantly being moved toward this center point of the map based on this force.
I see Erin laughing because she could figure out what's coming here.
this crashed the server, and the programmers said, please don't do this.
Please never do this again. We are not a supercomputer.
I was just waiting for the phrase, and then everything broke.
Yes, yes, because as you're well aware, once you are too close, the forces involved are so extreme that the numbers are too big. The magnitude is so great that you can't model it on your typical gaming computer.
No, I didn't realize it crashed servers so bad that programmers got involved with you. I thought it would just took out your own computer.
Well, I would work in the development environment and it would cause the server to crash. And I said, "Whoa, that's mysterious. I wonder why my server is crashing." So I went to some of the programming team and said, "Hey, why is my server crashing?" They went, "Because you're trying to model a black hole, stupid. Stop it."
Oh, that's fabulous. Okay, so let's talk a little bit about why those numbers are so astronomically high. But before we get into that, let's do a little bit of, just in case those of us who are watching, and certainly not your host moderator, are a little bit unclear on the science. I did bring some reading material this time. I brought along General Relativity for Babies, which is one of my daughter's favorite books. So if we need any visual aids, I have those. But for our science team, let's start with the most basic question. What's a black hole?
Go for it, Phil.
You toss that one to me?
Toss that one to whoever.
A black hole is a hole that is black. It's a...
well, good panel, everybody. Bye.
Yeah, thank you. Good night, everybody. A black hole is, a lot of people think it's like this incredibly massive object, and it doesn't have to be. It's not so much that it's massive, is that it's small. It's very, very dense. If you take some amount of mass, like a star, and squeeze it down until it's very, very small, the gravity of it gets so strong that not even light can escape. I am skipping over some essential physics here, but that's sort of the one sentence version of it. And so since light can't escape, it becomes black. The other problem is the gravity is so intense that if you fall into it, you can never get out again. So it's like an infinitely deep hole. So it is a black hole. Literally, it's one of the few astronomical objects where we named it, and the name actually makes sense.
Yeah, I think a lot of misconceptions that people have is this idea that black holes go around our star systems, galaxy, universe, vacuuming up everything in their path. And it's really not that. It's just this fact that you have this deep gravitational well that if, like Phil said, if you fall into it, you're not coming back out. But, it's just, you would orbit it normally. Just if you were far enough away, you just can cross under this event horizon where you definitely cannot escape.
And that's what an event horizon means. It's just the part where the gravity is so high that you can't, there's no way you could put an escape velocity in, right?
Pretty much, yeah.
Okay.
That your escape velocity is now greater than the speed of light, and you in trouble. And you mentioned too, because like when Jesse was talking about developing the story using the Newtonian physics of you have a mass, it falls down as a force by the distance squared. That's a fundamental, works for most of the time way of looking at gravity. But then you mentioned the general relativity for babies, and it's easier to think of a black hole using general relativity with that trampoline idea, that you have this really dense, heavy, small object that's pulling down. It's created this deep, steep gravitational well, and it's really modeling that is where everything breaks.
Yeah, to expand on what Erin said even a little bit, I mean, she made a very, very important point that the gravity of an object that you feel from it really, and this is something that Jesse mentioned earlier, depends on two things, and it's the mass of the object and how far you are from it. And so if you have, say, a black hole that has 3 times the mass of the sun, which we think is sort of the minimum you can have, it behaves exactly like a star with 3 times the mass of the sun, as long as you're far away from it. And so using Isaac Newton's equations for gravity, which we've been doing for 400 years, that works great. But when you get close to it, things start to get wonky and space gets really curved and time flows differently. And that's where general relativity comes in.
So explain to me a little bit. You know, again, I've read this book cover to cover many times, but there's only 7 pages, so. um, so I know that if you get an object with mass of any kind, and any kind of mass warps the space around it. When you get a massive enough object, it really starts to warp space to a noticeable measure. But what does that actually mean, that space is being warped around a massive object? Erin, you want to jump on it? Go ahead.
It's this idea that it's not just space, but space-time is being warped. That we think of our universe as a 4-dimensional fabric in space and time. So like you said, when you get close enough to it, your space is being warped in the sense that, you know, as you're falling in, you start to stretch out a little bit. You get these weird, we're so on the cusp of like getting into really complicated general trying to
for babies, Erin, for babies.
For babies. So you have that sort of visual stretch, but then you also have time dilation that happens, and I think we've seen this in other franchises as well, or other sci-fi movies.
They had that great bit in Interstellar about it.
Right. Orbiting a black hole at a distance, frankly, way too close to have that level of time dilation. But, you know, to an extreme degree, you see that time dilation.
Yeah.
You can get so much right in a movie in sci-fi, and then sometimes you just miss that one thing.
Though it's interesting that you bring up Interstellar, because our environment artist who created the black hole had actually just seen that film and said, wow, they really did a bang-up job of modeling an idea of what you might see when you're near a black hole, and that really inspired him when he went to build the black hole visuals for the accretion disk in our own level.
So the accretion disk really fascinates me, because as Phil was saying earlier, it's a black hole. Light can't escape it. It's just a big dark spot. But in both our model and in the Interstellar one, which as I understand it was made by, the most up-to-date calculations on the most super of computers, there's this big shiny ring around the edge of it. What is that Hollywood magic, or is that something that we actually believe is there around black holes?
Aaron?
Either
one of us could answer this, right?
Yeah, so, sorry. I'm just throwing when I have a science question, I'm just throwing it out, and whoever wants to jump on it can jump on
That's fine. Up until I have to name drop LIGO just because that's my baby, but up until LIGO detected the black holes merging without any electromagnetic component involved, the way we'd seen black holes before, because people would get confused with the LIGO announcements of being like, or even when we got that visual of the event horizon just in the last couple of years, people were like, but we've seen a black hole before. But what we were really seeing was predominantly X-ray emission from accretion disks that was in binary systems that are basically still in the process of falling into the black hole and heating up as it's falling in. So you just get that friction aspect. And as it's heating up, as it's falling in, it's emitting very bright, high energy X-rays. And so that's what we're able to see. And so when we see these accretion disks, it's because there's still stuff around that black hole that's continuing to fall in. But Bill, I don't know if you want to add.
Well, just that every time I write about this stuff, and I write about it a lot because as far as we know, every galaxy, like the Milky Way, Andromeda, all these other galaxies, they have a supermassive black hole in their center. And a lot of that stuff, we're talking millions or billions of times the mass of the sun. Stuff falls into it. As that stuff sort of falls in, it forms this disk, and that gets very hot and bright, like Erin is saying. And the thing is, people get confused because they say, well, how can that light get out if it's near a black hole? And I have my black hole model here. It's a squishy black hole. I don't know if they really do this.
Who knows what happens in there?
Back in the day when this is a NASA mission, the Gamma Ray Large Area Space Telescope is now called Fermi, and it observes gamma rays. The material, as it falls in, there's this volume around the center where the escape velocity equals the speed of light. Anything inside of there cannot get out. But if the light is coming from here, it can, right? The escape velocity is lower than the speed of light, so light can still escape. So that accretion disk is around the black hole, but not inside the event horizon, so light can get out. And in fact, these disks get so bright, especially around these supermassive black holes, that they can outshine the galaxy. They can actually outcompete 100 billion stars. And we can see these sorts of active black holes basically clear across the universe.
That's amazing. So correct me if I'm making an assumption here and I may be totally wrong. Is the disk that you see then light orbiting the black hole?
That's a little different.
A little different. Okay, no, I'm totally off base.
There's sort of the accretion disk, which is far out from the black hole.
Okay.
Like pretty far out. As you get closer and closer, the gravity gets strong enough that a beam of light can come into the black hole. I guess I could do it this way. Could come into the black hole and go around it, get bent by the gravity, and come back out again.
Okay.
And there's a point close enough to the black hole that the photon can't. The escape velocity is still kind of less than the speed of light, but because of the general relativity physics, and I'm sure Erin knows more about this than I do because my GR is a little... that photon can orbit a couple of times and then fall in.
Okay.
But that's generally closer in than where you see the accretion disk.
Cool.
Right, and if light, a photon, a particle of light is orbiting, that's not something we would see, because what we see is the photon that has escaped and has reached us. Which I know is kind of hard for us. It's when you have to get into that, like, what are we actually seeing?
Yeah.
Right. To know about a photon that's orbiting, we would have to bounce something off of it, which would then change its orbit.
God, yes.
Yeah, the photon is the light that we're seeing. So yeah, it's confusing. You have to actually kind of twist your brain around a little bit to.
And this does raise an interesting point about stuff that we couldn't do in the game. And for most of the players out there, you know, this is close enough. Oh my gosh, there's this giant black space in the map, and it's sucking my ship in if I'm not careful. But if we wanted to really model this thing like a black hole, then your phasers should bend around it. When you're firing at an enemy ship, you should actually be able to arc a shot around it.
Oh, that would be
the
cool.
bullet.
Not only that, but you could get crazy with this, because you could also play with the time dilation aspect.
Yes.
The light has been slowed down as it's trying to escape, so you'll see slightly frozen or slowed down images back.
So I wanted to do that, but unfortunately that was another thing our servers couldn't handle well, because we actually can cause our servers to model having different levels of speed, but when you do that, it affects everyone equally. Instead of saying this player is experiencing this kind of frame rate and that player is experiencing a different frame rate, so we weren't able to get that relativity differential in, sadly.
Relativity. Yeah, it's so funny, because like, it's just talking about this reminds me of the fact that, 15 years ago, I remember being in a seminar where someone who worked in numerical relativity, which is the field of modeling all of this warping of space-time, they were working on modeling colliding black holes. So just the merging of these. And the big seminar was the fact that they had completed one full rotation without their computer crashing. So it's like, it's impressive with how, and that was just 15 years ago. So there's like two things to be excited about. One, it's really, really hard to do. And two, computing has gotten so much better since then, just in those years.
It's amazing the utter leaps and bounds we've managed to take in technology like that. So Jesse, I want to talk a little bit about sort of the story of Gravity Kills, which is, I've played it a bunch, so I should know it a little more than I do. But I also play it a bunch, so I started skipping the text a little while ago, like a fool. So I know the Zenkethi are in orbit of the black hole, and they've got these bases that we're trying to unmoor and descend in past the event horizon. But why are they there? What is it about the black hole that they're searching for?
They actually have bases that are set up around the black hole, and the bases are not sucked in because they have gravitational anchors, also known as technobabble. And so the story is that the Zenkethi have been using proto-matter devices, the Genesis wave from Star Trek, in order to fight planets that have been infested with their enemies. And in order to make these weapons, they need certain kinds of super exotic particles, where exotic is a stand-in for this is some Star Trek hand waving. And the particulars in this mission is that they are capturing Hawking particles, and this is also a dodge based on the fact that black holes are hypothesized to emit Hawking radiation, but the levels of such radiation are theorized, from my understanding at least, to be so low that I don't know that it would actually be practical as something that people would harvest. But this is the 25th century, and we're doing some entertainment fudging here. But that opens the door for perhaps Erin to talk a little bit about the Star Trekification of this kind of physics, or for Phil to talk a little more about Hawking radiation.
Yeah, that's exactly what my follow-up question was going to be. So, science team, go!
I do want to hear Phil's take on Hawking radiation. So.
Oh gosh. Well, have you read Hawking's original paper on that, Erin?
Yeah. Yeah.
Okay.
I have opinions, but I'm a general relativity person. So.
Right, and I'm not. My studies were always about exploding stars, which form black holes, and at that point I was like, I'm done.
No, we're done.
That's where she starts. And I read Hawking's original paper, and it's like, the first paragraph I'm like, oh, okay, sure. And the second paragraph I was like, well, I guess I get this. And then the third paragraph's like, I have no idea what he's talking about now. It gets pretty serious pretty quickly. The problem is that black holes are relativistic objects. Their physics is described by general relativity. However, we also know that quantum mechanics is a description of the universe as well. It describes things that are very small. And we know that works. And we know relativity works for very massive objects or things moving very rapidly. The problem is quantum mechanics and relativity don't talk to each other very well. They don't overlap well. We don't have a theory that sort of overlaps both of them.
Some sort of unified field theory.
Kinda, yeah. And it's fiercely complicated. But Hawking sort of proposed that at a quantum level, a black hole can actually emit radiation. It has to do with the uncertainty principle and all this complicated stuff. But that over time, you could have particles near the event horizon. You can have sort of a spontaneous generation of energy from a black hole. Part of it falls in, part of it goes away, gets sent out into the universe. And we see that, if we stand back far enough, as the black hole emitting radiation. I'm oversimplifying this, probably past the point where it's correct. But that's sort of the idea. And this depends on the mass of the black hole. So these supermassive black holes emit radiation very, very slowly. Lower mass ones emit them more quickly. So actually, if you're looking to harvest these particles, what you want are quantum black holes, little tiny black holes that maybe were created in the Big Bang. Or maybe, don't Romulan warbirds use some sort of weird singularity?
Yes, they have a singularity drive.
Generation. So there must be some way of making them. You can do that, but in for the game's sake, that I guess that's sort of what you're doing here. But I'll toss to Erin, because that's where my knowledge kind of ends.
Yeah, I mean it's interesting because I think it's, again, similarly tried being the operative word for reading that Hawking paper, that I think everyone is just like, too smart, don't understand, must know what he's talking about type thing. But I mean, for me, because I come from a general relativity standpoint, viewing gravity as a force that needs to be shoehorned in with these other three forces that are easily unified, I sometimes err on the other side of that, of being like, dude, guys, it's just the shape of our universe due to the presence of mass. We don't need to try to find gravitons. We don't need to try to unify. Thinking of gravity as a force, I think, was like this 400-year-old red herring that we've continued to chase because it's worked so well, because it works for so much stuff that we've been able to see and test and prove here on Earth, that then trying to find some particle associated and trying to unify it with the strong and weak and electromagnetic forces, I think is personally a bit of a futile effort. But I have to make that very clear that this is just kind of the way that of studying general relativity for a long time. I'm sure there are plenty of quantum physicists out there watching this just kind of being like, twitch. Yeah. But I think that this idea of Hawking radiation, for me, I don't necessarily see, I can see the theory behind it, but I don't think it needs to be accepted one way or the other. I think it's an interesting way of thinking about what might happen to particles at the quantum level as they fall into a black hole. But I do think that it's hard for us to be able to say definitively that there is Hawking radiation or there's not Hawking radiation. And I think we have to get a better understanding of the quantum physics to be able to come up with a good way to definitively say, yes, we found it. But from my now happy place, that's the place that made me cry, which made me pivot toward working in making up terms. I think, exotic particles are so funny because you can use that exotic matter exists in a particle physics standpoint. When we talk about exotic matter, that is sort of this umbrella term in the particle physics realm for particles and matter at the sort of subatomic level that behaves differently to the way that we see matter react normally. But it's great for technobabble.
Yes.
I kind of want to throw a technobabble challenge at the three of you, but we'll wait till later on in the stream and do that. I surprised Erin with one of those last time.
Which I gotta say, I was pretty proud of.
She supplies the technobabble for the show, so I'm not so sure.
Maybe I'll have you two go at it and have Erin judge.
One thing I did do in the mission that I'd love to hear our scientists speak on is the mission talks about, okay, this is a black hole. It's going to be constantly exerting force on you, and once you get past the event horizon, you are going to be spaghettified, and you and your crew don't want that. And there's a point that you can get to on the map where it pops up a warning and it says, okay, we're hitting the point of no return. Impulse engines cannot get us out of this gravitational pull anymore, but we can go to warp right now because Star Trek ships can go faster than light. So theoretically, they could escape an event horizon, and they have structural integrity fields, so they might survive spaghettification for a little while. Maybe not, I don't know, but it made for great gameplay.
It made for great, if you accidentally go too far ahead, you don't die forever, because there's no way we can explain this.
Well, now, Erin, if you're really close to a black hole, can you create a stable warp bubble? Because I think the stretching of space is going to really mess up your equations.
That's pretty much what my assumption is that if you had a warp bubble before you reach that point of no return, the physics would be a little different. But in this case, talking about being at maybe, because I've heard this used a lot before with sort of black hole orbit dynamic stuff, that you have the green zone where you don't need any energy to get out, that you orbit it happily as if it was just any mass, that it's like us going around the sun. That's sort of the green zone. The yellow zone is the area where you could escape, or to stay in orbit you have to constantly be exerting some fuel. And then that red zone is really not the event horizon, but your point of no return as a massive object. You're not going to be able to get out of that. And so I can see that being the same sort of thing where space-time at a certain point has become so distorted that the energy required to build a warp bubble around your ship and get out is not going to happen. So I'm all good with that. I think that's awesome.
Yeah, and if you don't hit that big red button, your ship does get drawn in and spaghettified, and you get a special accolade called "Everything Sucks."
I wonder if the spaghettification is a different map that sort of overlaps that. I mean, I can use the black hole here, and I've got a little Earth bubble, Earth guy here. And the thing about spaghettification is, if you get, sorry, I've got things rolling around on my desk. If you have a black hole and you have an object, say a planet that's near it like this, gravity gets stronger the closer you get to the black hole. So this side of the planet is getting pulled much harder by the black hole than this side. And when you work out all the physics, that basically is stretching the planet this way. And when you work out it actually gets very complicated very quickly. But that is what spaghettification is. The closer you get to a black hole, the stronger this shear force is. It's trying to pull you apart. And your ship, you have a hull which has a certain amount of strength to it, but it's like trying to stretch like taffy. And as you get closer to the black hole, that gets worse. And part of that is because of the curvature of space-time, the way space is getting warped. You can think of it that way as well. And I'm guessing those are two different things. Spaghettification, which is the structural strength of your ship, versus the curving of space, which is not allowing you to make a warp bubble. And if you really wanted to dive into that would get really complicated really fast. But both of them suck because your ship is starting to get torn apart and you can't get away. So that's bad.
That
So,
could be
yeah,
a
there
really
you go.
interesting kickoff point for a story where, you know, you try to create a warp bubble when you're too close to a black hole for the warp bubble to work, and the folding of space-time takes you somewhere because it's Star Trek, and you find, you know, it's some alternate universe or slowed down point in time. Actually, yeah, could be really interesting.
Because when I was sort of caveating it with this idea that you have to form the warp bubble at a certain point versus already being in one, that was where my brain was thinking about like wormholes. Because in the theoretical physics realm, the geometry of the entrance to a wormhole looks a heck of a lot like a black hole, that you get that steep gravitational gradient. And in Star Trek, we happily pop in and out of wormholes all the time. So,
it's a day trip from Deep Space Nine.
Yeah. So I wonder, I mean, I think personally the best visual I've ever seen of a spaceship going through a wormhole was literally in Galaxy Quest, because they spaghettify the ship as it goes in and then de-spaghettify as they pop back out. But yeah.
There is one other problem that the spaghettification causes that I didn't solve, but presumably Star Trek magic would handle, which is that when you're experiencing that much tidal force that's pulling, if you've got, say, a tritanium hull or something like that, and you are experiencing cosmic tidal stress that's pulling it like taffy, it's going to heat as the molecules are literally being yanked apart by these immense gravitational forces, and that breaking of molecular bonds is releasing energy in the form of heat. It would be like if you took a piece of steel bar and you just had something strong enough to yank it apart, it would actually superheat in the middle.
That's fascinating. So I have a question about spaghettification, and it's another one of my I'm the guy on this panel who doesn't know science questions. So you know, the cartoon version of spaghettification you always see is, you know, the Galaxy Quest thing where everybody gets turned into taffy and super stretched out. But the way Phil was just describing it, the forces pulling on you, say you were as a person, or let's say a starship to make it less gross. Say a starship would start to get spaghettified. The ship itself would break apart long before the cartoony spaghettification happened, right? Okay, I'm seeing nods. Good, I'm understanding something.
It's worse than that even, because you're being pulled because that sort of in the direction directly away from the black hole. We would say that's the radial direction. One end of the ship is being pulled harder than the other, but there's also a compression that's happening as you're going into it. From the sides, you're feeling the squeezing force, and you're being pulled this way. So, yeah, it's bad.
It's not great.
It's taking a piece of clay and rolling it in your hands, basically.
Yeah, actually, while also stretching it at the same time.
Yeah.
Oh God.
I really like your. Let's make it a starship so it's less gross.
Yeah. Well, because I started thinking about my feet getting torn off, and I was like, I'm not going to think about that anymore. I'm going to inject that thought into a black hole.
I think it's interesting because it brings up, you know, some question I get asked all the time is like, what happens inside a black hole? Like, if you fall into a black hole, what's going to happen? And it's really looking at how strong those forces are to the point where it's like, could it tear apart the molecular bonds, you know, or the atomic bonds, and break you down, overcome all of those strong and weak nuclear forces that to hold atoms together and just convert into energy. And you know, there's various things. It's all very in the theoretical physics realm because it's hard to model that.
With
in my headcanon in Star Trek, black holes are the back doors into the Q continuum.
Oh yeah, that makes sense. With the okay, another silly question from the Mike Factory is if atoms were getting torn apart at the atomic level inside a black hole, would that be creating 100 million atomic explosions all the time? And would those then be just sucked up into the black hole because it doesn't matter how big the explosion is at that level of gravity? I'm going to go back to regenerative for babies. I'm sorry.
No, but I think that's kind of what I was implying with the comment of like, we're not 100% sure exactly what those forces are once you get beyond the event horizon that we literally can't see, knowing what because you're then in such an extreme realm of physics. Yeah. And that's, I think, too, why when we talk about the Hawking radiation and trying to find a way to bring quantum physics in with general relativity, there's a lot of unknowns. I think if you're talking about what happens at the subatomic level, within the event horizon, it's a lot of, huh? I can come up with something based on physics principles, but there's a lot of assumptions associated.
Yeah,
with
physics
that.
principles tend to change in there.
And honestly, in one sense, I would say, I don't want to say realistically, but on like the macro level, on like I'm commanding a starship level, it doesn't matter because A, you're dead. And two, once you're inside the black hole, I mean, but you got to realize that when you say the escape velocity from a black hole is the speed of light, it's essentially saying you are moving at the speed of light when you pass the event horizon. And it's more complicated than that, but if you're just falling straight in, that's what happens. So even if the black hole is a supermassive one in the center of a galaxy, you're talking about an object that's not terribly big, and you're moving extremely quickly when you pass the event horizon. And if it's a stellar mass one, it's only a few miles across. You're literally going to go from the event horizon to the center in a millisecond. So the amount of time we're talking about isn't very much.
Fascinating.
All that's left behind is the sound.
Oh, and time and space don't mean what they mean inside a black hole that they do out here, and it's a mess.
I think
that was the other part I was
that.
going to mention, was that the general relativity time dilation plays a part there, and so and this is again where it's getting above my pay grade. I'm just a game designer. Like, you get to the center of the black hole or beyond the event horizon effectively, and you're now like in infinitely dilated time. You know, how is time moving with respect to the rest of the universe? And then you can get into the weird information theory stuff of, does it really even matter since you can never get out to interact with the universe anyway?
Yeah.
How much do we actually care what happens?
Yes, you did. Press the respawn button.
Yeah. The respawn button's in the black hole? That's so good to know. When was my last save point? Was it before 2016? Oh, God. Okay, so
Right.
I have one more general black hole question, and then I want to talk a little bit about video games and using science. But I wanted to talk to Erin a little bit because I know this was her thesis. I'm going to read 2 pages now from General Relativity for Babies, the entirety of the entry on gravitational waves, which is: 2 black holes can spin around each other. They send ripples through space called gravitational waves. And that is the entirety of the entry on gravitational waves. So, Erin, what's a gravitational wave?
I mean, that was exactly it. No, so it's so the gravitational waves really are ripples in the fabric of space-time that are caused by any asymmetric mass moving. So me doing this is good, technically sends out gravitational waves. And so essentially, Einstein conceptualized the mathematics of general relativity, and then basically did classic Einstein and was like, well, what if? And what if something changed and introduced a small perturbation? So basically just said, let's say a star explodes, or let's say there's some movement that's going on. We're just changing space-time slightly at a local level. What happens? And propagate that change all the way through the math, and you end up with a wave equation that's traveling at the speed of light. And so that's where you see, okay, so when there's a small perturbation, that information travels like a wave at the speed of light. So Einstein said, all right, so the math shows this, that these waves are present, that are physical ripples in space-time, but they're so small, no one will ever detect them. And so that was sort of the baseline assumption. And it wasn't until like decades later that people went, well, how could we detect those? Like, could we actually see space-time itself rippling and moving? And then decades and decades after that, building these interferometers that move such that one arm gets shorter, one arm gets longer as a gravitational wave passes by. But these are fractions, 1/1000th the size of an atom from the most violent explosions in our universe, which are colliding black holes. You get these two black holes, which are huge distortions in space-time, spinning around each other, then they merge, and you get this huge ripple in space-time. It's like throwing a pebble into the pond. It sounds simple, but that's pretty much exactly what's going on. And those ripples travel, and they get weaker and weaker as they're traveling. And it's this distortion in space-time. Now, again, it's not a wave that you could ride. We've seen
My Silver
some
Surfer
Star Trek
dreams,
episodes.
they're dashed.
It's a wave that could kill you if you tried to ride it. Yeah.
Yeah. They compress, and but we'll give science fiction a bit of a pass on that. It's gravitational waves. It sounds cool.
So it's rippling space and time. Obviously, because they're everywhere, when they've passed through us before. But if you're close enough to one, do you actually like feel that shift in space time, or is it just kind of like, oh yeah?
Yeah, but you have to be really close. It's since it's hard to convey when we talk about general relativity and space-time and all of this stuff. We always use that trampoline analogy. We always use this, to see these ripples. But space-time itself is a really rigid fabric, if the way you want to think about it. So those ripples really are tiny. It's instead of thinking about it like a trampoline that you can easily jump on and bend, think about it more like, the parachute cord or something. Like this really, really tight fabric. And so you have to be very, very, very close for it to have any sort of physical impact. But gravitational waves are passing through us all the time. When they made the LIGO announcement, it's one of the funniest animations I've ever seen, because they showed how these gravitational waves pass, they occur, and then they travel through the universe, and then they hit the Earth. And just on the bottom of the video, it says, scale is vastly exaggerated, because they're showing the Earth doing this and it's going by. So technically, yes, but you'd have to be, from a scale, you'd have to be next to it to actually have a discernible effect.
At which point we go back to Phil's, you're dead anyway, so what do you care? So, Jesse, we talked a little bit about the process of implementing this, and we've gone deep into sort of the science of black holes. But, Phil and Erin, feel free to jump in on this too. But when you're approaching making a video game, you kind of have to find that balance between, realism and fun. And it's something that you mentioned you had to do in terms of not crashing the server when creating your black hole model. How do you, especially for a sci-fi series like Star Trek that's so, excited about being hard science, how do you walk that line? What do you kind of think of when you're designing content for the game?
Well, with Gravity Kills in particular, it started with the science of saying, okay, black holes are a thing that we have theorized exist, and they function in these ways that cause all sorts of interesting phenomena. And so how can we take that interesting phenomenon and turn it into a story or a game element where the player interacts with that, where that has an impact on what you're doing? And the movement, the force that's exerted by the black hole in Gravity Kills effectively is something that's forcing you to pay attention to it, and it changes how you play the game. It's not just a typical open space map where you can fly around at will with your impulse engines and fight things. You are now constantly aware that you are being pulled, and that the rate at which you're being pulled gets faster, and the pull gets stronger as you get closer. So that informed things like the decision that the Zenkethi stations are spaced so that the first one that you destroy is furthest from the black hole, and as you're working your way down the map to destroy additional stations, they're closer and closer. So the gameplay is getting ever tighter, where you have to worry more because those gravitational forces are stronger. So the science gave us the inspiration of, here's this amazing thing that we've conceptualized, that we think about, and that we've turned our instruments toward the skies, and we've seen evidence that suggests that these things actually exist out there and behave in these ways that we can model. And then say, okay, so in the context of a Star Trek story where you're flying a starship and doing these things, how does that impact your story, and how does that impact your players' choices? How does it make them respond to this map? So that it's not just a piece of scenery that's in the backdrop, but it's something that actually changes how you're playing the game. And I'm sure that Erin could say that in Star Trek, there's many ideas that come from science that are driving what is the story, how do the characters respond to that.
And then there's some stuff we just make up, like anti-time.
That was cool. I like that.
Yeah. Well, like the whole conceit of the Zenkethi harvesting Hawking particles, which is again eliding off of Hawking radiation, which harvesting Hawking radiation in and of itself is kind of pushing the edge of that concept. Is like how Star Trek used tachyons extensively in the 90s, and tachyons existed essentially as a mathematical placeholder for some equations where we said, well, to solve this sort of thing, we have to hypothesize the existence of a particle that moves backwards through time. And I'm with the caveat that, again, I may not be completely up to date. My understanding is that in the modern interpretations of physics, we're fairly certain that tachyons aren't a thing, but they made for great storytelling moments.
Yeah, I love the way that the 90s Star Trek used tachyons, because it's really this idea that they are, because tachyons exist outside of the Star Trek realm. They weren't a made up term for the use in Star Trek, but they're, again, I'm going to use a phrase. There's people who think that it's not the correct way to think about them, because you could say it's like they have imaginary mass or negative mass, or there's lots of kind of different ways to think about them, but essentially instead of dipping space-time, they invert space-time, and that as a consequence means they always travel faster than the speed of light and break all causality, which is great for science fiction. We're talking about time travel, warp drive, anything like that is breaking that speed of light limit. To just say there's tachyon residue works great.
Oh, I got it all over me.
Oh God,
it's everywhere.
Oh God, now time is exploding out from me.
There's always an idea that in science fiction where you let the science inform what the characters are going to do, and it's at some point it becomes an easy way out of a situation. Oh, we'll just, Star Trek became famous for this, right? We'll invert the tachyon field or whatever. But there's a lot of science, like, for example, if you see a bunch of bases orbiting a black hole, you could tow an asteroid, say, or some massive object, drop it into the black hole. When it gets torn apart and forms a transient accretion disk, basically just a temporary accretion disk, that gets superheated and blasts out X-rays and gamma rays, you could do that to blind those space stations and then just pick them off at your leisure. And then at some point, the writer of the show goes, well, that's too easy. Where's the drama in that? Well, it's awesome, right? But yeah, it's no fun. There's no gameplay really involved there. So there's a give and take between what you can stick with real science, which of course you don't have to with Star Trek. You can add in imaginary science, which is too easy, but it's always got to play into the story itself, and you always have to worry about that.
Yeah, and I'm sure, Phil, you've had to deal with this too in some of the other shows that you've worked on, but when you get that good science explanation that has that good amount of drama versus, answering the issue, you have to then draw a line on how much you have to explain it. That if you say, to explain, we're going to tow the asteroid, which I love, we're going to tow the asteroid here, it's going to tear apart, we have this transient accretion disk, it's going to emit all these gamma rays, and then you see the writers like glaze over. It's like, okay, the audience will probably do that too. It's a really cool idea, but we have to think of how to make it interesting too.
Yeah.
That was never handled better than in the movie Inner Space. 80s, 90s, I can't remember.
I think 80s.
A long time ago. And just a scientist is going to attempt a very complicated thing, and he's saying, well, all I have to do is this, and the other character says, wow, how are you going to do that? And then they cut back to the first character, and he's like surrounded by books, and he's doing all this stuff, and he goes, it's complicated. And I was like, okay, I buy that.
That's
good.
Perfect.
Move on.
Yeah. Go ahead, Jesse.
Sorry, I was just going to add that, to me, really interesting science fiction that's distinct from fantasy with space as a backdrop always takes a premise of how does our understanding of science and scientific principles inform how we approach our universe, or change how we live as people in the future? Or how can we take things that we've hypothesized today and project what that's going to do about our lives tomorrow? And Star Trek, of course, is all over this, saying we're going to take these ideas and project forward 300, 400, 500 years and say, what is the effect of these things on human lives? Or the other way around, man versus nature, or woman versus nature, or whoever versus nature. The idea of, we've encountered this phenomenon that was hypothesized by physics, or that we never expected to encounter with physics, but how can we get a scientific understanding of it?
Very cool. So I guess my follow-up question to that for all three of you would be, what sort of advice would you give somebody who's stepping into the field of creating science fiction that wants to, make it good science, but maybe doesn't have a degree in astrophysics or a friend they could call on the phone who does? What level of research is the right level of research, and how do you make those kind of stories that walk that line?
Yeah, I was on a panel once that was kind of about this topic. It was about, for science fiction writers, how to resource science. And I was like the outlier. It was all science fiction authors who talked about what their process is and how they approach this. And the issue that I think a lot of people run up against is trusting, when you do a Google search, what is a good source.
Yeah.
And understanding that, even you might think like Wikipedia pages are a great place to go, but some of the science Wikipedia pages are heady.
Yeah.
And may not be easy to interpret properly. So I think the thing that will upset me as a sci-fi fan and a scientist is when stuff is so simple that they shouldn't have got that wrong. That it's something that, you call a star a black hole or something like, or one example I use all the time is interchanging galaxies versus star systems. That's the one thing that will send me into an apoplectic rage about anything. I can turn my science brain off a lot, but when that happens, I lose it. And so it's things that really could have been answered in a quick Google search that you'd get millions of responses, that there's no question that that's what that is. Everything else, I think, especially if people don't feel like they have the friends or resources or a Twitter DM away that they can call, just making sure those basics are solid. That'd be my advice.
Yeah, I agree. And I having talked to a bunch of writers and producers and stuff like that over the years who are trying to make the science right but still get their story right, I always say, look, you can sacrifice the science for a story. I can always come up with something, some gimme, some MacGuffin, which will get you from point A to point B. The thing is, it's got to fit in the universe right. The audience, you can't pull one over the audience that way anymore. Back maybe in the 60s, you could say, oh, it's this. And everybody would go, oh, that sounds science fiction-y. I'll believe it.
Reverse
Nowadays,
the polarity of the neutron flow.
You don't want to draw them out of the story and have them go, that doesn't make sense. But it's fun to hear a writer say, what I want to have is this happen. Can I make that happen with, an asteroid impact or a solar flare or something? And it's like, well, no, but what you might not know about is this. And then they go, ooh. And so it's lovely to see these writers wanting to get the science right. And that's great. And that'll get you so far. But in the end, it's like, don't fret about it too much. Just make sure it works and that it doesn't come across too much as a, and then God came in and changed everything and then, everything's fixed.
Yeah. And I think, Phil, you probably have had to deal with this too, where you have writers who are so dead set on being like, well, I want it to be, we're going to have a solar flare. Like it's going to be a solar flare. And you're like, but solar flares don't work that way. So it's like, let's just make sure that we don't say anything explicitly wrong, as in a solar flare is this. Let's just gloss over that. And then at the end of the day, to allow yourself to sleep at night, it's just going to be like, all right, this is really what they want to do. I'm not the writer. I am just to advise. I have advised, and I know it will only anger that much of the audience. And that's how I'm going to choose to sleep at night. And it can be really, really hard sometimes, but we just, I'm not the writer. I'm there to help and answer questions, but if they want to take it somewhere,
yeah, exactly. And I bet you've been in the same situation too, that I have so many times. You're watching a movie and something weird happens and you go, yeah, I bet that was already written. And then they talk to the science writer. I've watched movies which were, otherwise pretty good, but there's like a lot of really bizarre science in it. It doesn't make any sense, but it's clear that they had to sort of make up the science to get from this plot point to this plot point. Oh, excuse me, gravity. Gravity. Not any specific. No, actually, but as I watched, I loved Gravity. I thought it was a great flick as a human drama. But you can see where they had to get from point to point to point, and the science doesn't work. But they had to make it work to make the plot go. And it's like, and I'm okay with that. Actually, I'm making fun of it, but I'm okay with it because in the end, it's the audience experience that's important for a movie.
Yeah, this is the fiction half of the science fiction equation, is that you're telling a story and there has to be some sort of drama, something that has happened that has taken the story from point A to point B and caused some sort of change in the state of the characters or the universe that they live in. It's rare for popular science fiction to really be made with an eye toward being 100% accurate and educational. It's there so that these science conceits are telling a story. Like, there's that science fiction short story, The Cold Equations, which hypothesizes a guy on a little courier ship that has no margin of error, and he discovers that he's got a stowaway, and he has no choice but to eject the stowaway into space because otherwise he does not have enough fuel to make it to his destination, and they both die. And that's hard SF in the sense of like the physics has said this is what must happen. And that drives all of the drama of the story. But many, many, many of the stories in Star Trek and other science fiction franchises are inspired by science, but then the story comes out of the drama of the characters dealing with those science elements. As to getting inspiration for what science element is going to create that interesting conflict in your story, a good shortcut for writers who are new to the hobby or don't have those resources is look up some of the top unsolved problems in a given field, because those are the things that are big questions that a lot of experts are working on, and often they're in popular consciousness. Things like the NP completeness problem in computer science, or the three-body problem in physics, which spawned an award-winning science fiction novel. And you can get enough of an understanding of those that you can say, here's a big problem, and without having to solve the problem, it's not too hard to get enough of a general understanding that you can then build some drama around it, because enough people have looked at these problems, they're popular unsolved problems, that someone has done a breakdown page somewhere on the internet saying, in basic terms, here's what the three-body problem means.
That's cool.
I think probably the best example of that I can think of is Mass Effect, the Mass Effect series, where they have like a key component. It's called mass effect. The mass effect is caused by channeling a electrical current through this element that's called element 0 that channels dark energy and simulates an increase or decrease in mass. And what they're doing is saying, well, there's energy mass equivalence, E equals mc squared. We don't know what dark energy is, but we have this element that channels dark energy to simulate mass. And I'm like, there was enough logic that went into that and enough we don't know about dark energy that, like, I'm not opposed to that. I think that from a story standpoint is kind of brilliant.
Yeah, my wife is a physics teacher. I remember the first time she read the codex entry on how mass effects actually work. She sat there going, that makes sense. That makes... What? These never make sense. That makes sense. So we're coming up on the end of our time here, but I do want to do our Technobabble challenge. So we're going to have, Erin, you're going to be the judge, since I think Phil's right. You might have an unfair advantage here, an experience
and I did
level.
It last time, so
That's true. That's true. So let me come up with something really quick. Okay, so I'm going to come up with a problem. I'm going to give both Jesse and Phil 10 seconds to think about it, and then I will flip a coin to decide who goes first, and then Erin will decide the winner, who will win the adoration of all of the audience. audience today, and that's about it. So let's see. Following up on some of the stuff we've talked about today, let's say that the Starship Enterprise, we'll say it's the Enterprise F, so that you have all the most up-to-date Starfleet technology, is being chased by a rogue Gorn scientist who has discovered a way to create gravity waves in a gravity wave cannon. They bypass shields and hull integrity fields because it's a gravity wave cannon. The captain only has 10 seconds to make a decision on or I should say the chief engineer only has 10 seconds to make a decision on what to recommend to his captain before the ship is torn apart to pieces. All right, you guys have 10 seconds to think about this and go.
I've got one already.
Good. All right, I'm going to pull up my coin flipper.
And can I add in the caveat to make it clear that these are gravitational waves?
Oh, sorry,
not...
gravitational waves.
not gravity waves. Oh,
yeah,
nuts.
I know.
Yeah. Those are actually two different things.
My science advisor came in and changed the script at the last second, guys. Sorry, I don't know what to do.
There you go. It's a good team. It's a good team.
Okay, flipping. And Phil, you are first, my friend.
Oh, good, because I'm worried that Jesse would come up with the same thing.
Uh-oh.
The obvious solution, I would think, is to create a warp field around your ship, which then fluctuates, ripples itself in an anti-correlated phase with the gravitational waves coming at you, so that when the waves are coming at you, crest and trough, you make a trough and crest, and so that space remains constant around you. You are basically you're destructively interfering with that gravitational wave. Fabulous.
Jesse?
That's a brilliant answer because it's a more refined version of where I was originally going to go. So now I have to fall back and punt. Well, the first thing that we have to do is drop the shields, because as we saw in a previous TNG episode, gravitational waves get amplified when they strike the shields, implying that shields are some sort of actual bending of space and not just an energy absorption device. So we have to drop the shields, drop out of warp, and then generate a static warp bubble so that we can create our own area of space-time where we set the rules. Just like when Q said change the gravitational constant of the universe, and Geordi said we can use a static warp bubble to alter those constants. We're going to use a static warp bubble to get rid of those gravitational waves by asserting our own set of rules of physics in the area of space around the ship. And then we're going to continue propelling the ship by relying on soliton wave theory instead.
Oh, man. All right, Captain.
Babble in that one.
Captain, it's up to you. Which engineer's recommendation are you going to go with?
I gotta say, the throwdown of the term soliton. that's some peak, science technobabble. So maybe, I mean, it's because I like the anti-phase as well. I feel like we've got pretty good ones, but I'm sorry, Phil. Jesse wins that with the soliton. Right, the
That's
soliton.
okay.
Oh, fabulous. Congratulations, Jesse. You have beaten an actual science and fake science.
All right. It always bugged me when Geordi said, "Oh, we'll just alter the constants of the universe," and it's like, well, then why don't you make the speed of light infinite in this bubble, and then there's no speed limit, and then you can just go anywhere in the universe you want.
Well, right, but then
we did that in Voyager. You turn.
I was gonna say then you turn into lizards.
Yeah.
All right.
That's everybody's favorite episode, right?
So much.
Threshold.
All right,
Threshold.
folks. Well, thank you all so much for joining us. This has been a super fascinating and fun panel. I really appreciate it. Starting with Jesse and going down the line to Erin and then Phil, where can people find you on the interwebs if they wish to know more about you?
You can follow me as Jesse Heinig on Twitter, where I will routinely post about whatever comes to mind, especially about Star Trek Online. And of course, you should drop in and try our game because it's free.
Yes.
People can find me at Dr. Erin Mac, DRERINMAC on Twitter, and then that's also my Twitch handle. So you can find me on Twitch streaming various games and geeking out about science fiction.
Including Star Trek Online.
Star Trek Online. Yay, peer pressure.
Wow. And I'm Bad Astronomer on Twitter, and I write for Sci-Fi Wire, the Bad Astronomy column. But the best place is just to go to about.me/Phil Plait, and I have links to all my social media there.
just fabulous. Folks, my name is Mike Fatum. You can find me on Twitter at Ambassador Kel, and Star Trek Online is a free-to-play game. It's available now on PC, Xbox One, and PlayStation 4. Come and give it a try. You get to adventure in the Star Trek universe. It's great. Folks, thank you all so much for joining us, and I will hopefully see you all again soon. Bye-bye, everyone. Bye-bye.
Thank you.
Bye.